When the rubber meets the road, here's the story of friction. Okay, gang, friction is a force that causes surfaces to stick together. So at a microscopic level, most surfaces are very bumpy and irregular, like this one that you see here. So you can see all the bumps and crannies here. So what can we do to minimize friction? One way, of course, is to try to smooth the surface. We can do that by sanding. You know, when we sand a piece of wood that's rough, we can make it smoother. Another way, of course, is to lubricate the surface. If we apply some lubrication, the lubricants fill into the little nooks and crannies. So, the amount that materials stick together is called the coefficient of friction. It's given by this little Greek symbol here called mu. Mu stands for the coefficient of friction. It's a dimensionless unit with no units whatsoever. It's a ratio, a comparison. The higher the coefficient, the more the two surfaces stick together. The lower, if surfaces are easily sliding past each other. So let's look at the coefficient of friction. The frictional force that we're going to deal with is two types, static friction and kinetic friction, or sliding friction. Static friction is obviously for objects that are at rest. Objects that are not moving experience the force of static friction. It keeps an object in place. Kinetic friction is the amount that an object encounters when it's moving, and it always opposes the direction of motion. So kinetic friction is always the opposite direction in which the object itself is moving. So to calculate the force of friction, it depends on a couple of things. One, this factor called the coefficient of friction. Static, if the object on the surface's top is motionless, or kinetic if the object is sliding. The other factors, of course, are the reaction force, or the normal force. The greater the normal force, the higher the frictional force. So the more those objects are pushing down or back at each other, the greater they stick together. And so the formula is mathematically expressed this way. The force of friction is equal to mu times the normal force. Let's try an example problem. A 15 wooden kilogram block is motionless on a wooden table. Now the coefficient of friction is associated with the particular surfaces. So this would be wood on wood. What amount of force would be needed to get this block moving, to get it to start moving? We assume it's at rest. Well, the force of friction is equal to mu sub s, that's the coefficient of static friction, times the normal force. In this case, the coefficient of static friction between wood and wood is 0.42. Mass of the block, 15 kilograms, times 9.81 meters per second squared. The acceleration due to gravity, that's equal to the normal force. So the force of friction is 61.8 newtons. If a force of 100 newtons is applied, what happens? Well, we know that that's greater than the amount of force needed to get the block to start moving, so it will slide. So we need to find F net. So we need to find what the force of friction is now for mu sub k. The coefficient of friction for a sliding wooden block on a wooden table is 0.3. Notice it's lower once the object is sliding. So the force of friction is 44.1 newtons, and therefore we can find the net force, the sum of the forces in the x direction, as the applied force plus the frictional force. Remember, if the frictional force is in the opposite direction of motion, it's always going to be subtractive. It's always going to be this opposite sign. So the net force is 55.9 newtons. From there we can figure out the acceleration of this particular block. A equals F net over m. We get 3.73 meters per second squared as the acceleration of this particular block. Let's try a problem of a skier. So a 60 kilogram skier is sliding along a horizontal patch of snow with a constant speed. What force must be supplied to continue moving with this constant velocity? Remember that when something's at constant speed, it's in equilibrium. We call that dynamic equilibrium. We need to know what force of kinetic friction is. Since he is moving with a constant speed, he must supply exactly that amount of force to maintain his motion. Forces must be balanced for dynamic equilibrium. To calculate it, we use the force of friction is equal to mu sub k times the normal force. Notice how small the mu sub k is for wood wax skis on snow, 0.05. So the force of friction is 29.43 to keep him in constant velocity. That's what his legs got to supply. And that's the end of the show, gang. See you in class.